Hello everyone again and Bismillah. In this video we are continuing to design a PID controller this time in order to lead the plan to achieve the following conditions. We have a rise time condition, we also have the maximum overshoot condition, and we also have an additional or new condition, which is the steady state condition. We saw that in the previous simulation it was very hard to achieve a perfect dynamical response with no steady state error. And this is well understood because our system actually is a zero type system. I will be showing you how our system is not capable of achieving zero. It's physically or mathematically not capable of achieving zero steady state error. Let's just try the steady state error equation, which is ESS is equal to, using the final value theorem, we know that ESS is equal to the limit of S when it goes to or approaches this zero, of S times E, which is the error, times the reference. Okay, now you should know that the transfer function of the error of the system, this E is equal to 1 over 1 plus CP. Okay, just remember this and don't forget it because it's very important. And actually, so this can be written as, benefiting from this equation, this can be written as limit when S approaches the zero of S times, now we, open this fraction, 1 over 1 plus, we had the PD controller as 3.5, I guess, times S plus 20, and it was divided by S squared plus 3S plus 2. So this is the open loop transfer function. And times the reference that we are providing to our system is a typical step function of magnitude 1. So it will be its Laplace transform is simply 1 over S. Now this S cancels this S, and we are left with this expression. We know that S is going to 0, so this will be 0, this will be 0, this will be 0, and we are left with 1 over 1 plus 20. What is it? 20 over 2, isn't it? Yeah, 20 over 2. 20 over 2, which is 1 over 11, and it's almost it's exactly 1 over 11. Now let's just, okay, I'm sorry for this, 1 over 11. Now we know that ESS of our system is approximately equal to 0.091, which is greater than 0.01. Now, because our system is a zero type system, meaning that the transfer function of our system, the characteristic equation of our system, does not have a free S multiplied with it. So it's a zero type system, and all zero type systems with a step response will have some steady state error. In order to achieve this inequality, since this is not zero, the condition is not to bring the steady state error to 0. We might actually achieve it with very high gains, controller gains, maybe proportional gains. But this will cause a lot of inconvenience when it comes to achieving the second condition of the maximum overshoot. So instead of doing this, we introduce the integral action to the system, which is the I in the PID controller. The integral action actually gets rid of the steady state error. It almost zeroes the steady state error. Not always, but it almost zeroes it when the system is, for example, a first time system or zero type system, and you are multiplying it. You are adding the integral controller to it. Most probably the steady state error will be 0. So let's just proceed to write down the transfer function of our PID controller. It's written as, it's C, which is the controller, and it's written as Kp, the proportional controller, plus Ki over S, which is the integral controller, plus Kd times S, which is the derivative controller. We may also write this as, it's just a convention maybe, Kd times S squared plus Kp times S plus Ki over S. Now you may notice that we have introduced an additional pole to the system. And this is what I was trying to mention when I said we will increase, I didn't say it exactly, but I was trying to say this. We will increase the degree of the system. The type of the system will not be zero type. It will be first type, the one type, So one type with a reference of a step function, the steady state error is destined to be 0 or almost 0. So I'm not gonna design the PID controller from scratch. I'm not gonna design it from zero. We may do that in upcoming videos, but since we already have the KD and KP coefficients that satisfy our conditions, we will just put them, and we will have our PID as, I mean, it's equal to 3.5 times S squared plus 20 times S plus KI, okay, over S. Now, before asking that question, let's just write our new transfer function and have a look at it, at the change. I mean, I'm skipping the calculations. You can do them yourself. Just plug in the normal CP over 1 plus CP. It's the normal the standard transfer function of of a closed loop system. And it will look like 3.5 times S squared plus 20 times S plus Ki, and this is divided by S to the power of 3. Oh, you noticed this? I guess so. Plus 6.5 times S squared plus 20 times S plus Ki. Now, yeah, we might write it in capitals or not, yeah. So now you notice that the degree of our characteristic equation, this is our characteristic equation, I'll be writing it, it has been raised by 1 degree, so it's now of a third degree. It's a third degree characteristic equation, third order characteristic equation. And this means that we have added an additional pole to the system. I'm not gonna delve into the details of the control theory when it comes to the poles and zeros and so on, but I previously said that we added an additional 0 when we added the P controller, and now we are adding an additional pole. When we add an additional pole to the system, we actually may have some concerns about the stability of the system. Is this system still stable or not? This is a very valid and important question when it comes to adding a pole to the system. And in order to preserve the stability of that system, we may use the Routh-Hurwitz stability test or stability criterion in order to assess the stability of our system. Hurwitz, I think it's written like this, hopefully. And I'm not gonna, express, or I'm not gonna explain how is it written. You may have taken it in your control courses, but I'm gonna write it very fastly. It's 1, because this is our characteristic equation, so 120, then we have zeros, then 6.5, we have Ki in here, then we take this times this minus this times this divided by 6.5, which will give us 20 minus Ki over 6.5, and here we have 0 because we have zeros in here and in here. Then we will have Ki in here and a 0 in here. Now, from this criterion, we know that this array, which is called the Routh array, every element in this array should be greater than or equal to 0 in order for this characteristic equation to be a stable characteristic equation for a stable system. So 1 is greater than 0, 6.5 is always greater than 0, but we know that 20 minus Ki over 6.5 should be greater than 0 or equal to 0, Now this gives us, by simplifying everything, this gives us that Ki should be less than or equal to 130. And from this last element of the array, we know that Ki should be greater than or equal to 0. From these two conditions, we can combine them, from these two inequalities, we can combine them to get the interval in which Ki is a stable coefficient for a stable system. We may say that Ki should be greater than 0, greater than or equal to 0, and at the same time, it should be less than or equal to 130. So this is the condition that we have got for our Ki control. Of course, it's a very easy thing to do, but the transfer function of our controller will be something like C is equal to 20 plus 3.5 times S plus, we may select any kind of a value between 0 and 130. Let me select a small value, maybe 2 over S. Now, does this selection matter? Yeah, it matters. And actually, when we added the integral action, we cannot now deal with this transfer function as if it's a standard transfer function for a standard second order control system, because it's not a second order control system anymore. It's now a third order, and we do not have exact expressions about the third order. We have some approximations. Now, what I mean by this, we do not know exactly what's omega n, what's zeta, the damping, and so on, but we have approximations for them. But instead of giving those approximations, I'm going to simulate this system. Then manually tune the Ki that we need. We know its interval. It should be between 0 and 130, but I mean, in order to select the exact value, the exact suitable value for our system, we will be doing that manually using manual tuning. There are some robust methods, numerical methods to tune the parameters of PID, but no, we are going to use the manual tuning method because it's the simplest one and it's very intuitive when you get used to it. So thank you for listening and see you in the upcoming video.